All right, one of my favorite units in AP Environmental Science, Earth systems. So in mineral resources and geology, by the time you're done with this presentation, you should be able to describe the formation of Earth and its distribution of its critical elements amongst Earth, and define the theory of plate tectonics and discuss its relevance to the study of the environment, and describe the rock cycle. I know you're thrilled, and basically discuss its importance in the environment and its importance to environmental science. Essentially, as we saw from that hybrid electric car example, decisions about resources used, they're not always simple. And so why are some Earth's mineral resources so limited and others are not? And why do certain elements occur in some locations but not in others? And, basically, what processes create these minerals on Earth in the first place? And what are the consequences of yanking them out of the Earth? So, understanding the answers to these questions helps environmental scientists make these really informed decisions about the impact on the environment and the economic costs, and also the benefits of bringing up these resources. And that's what we're going to explore. We're going to explore how resources and geology and soil science are all related. And we need to take a very close inside look to explore Earth structure and its formation and the ongoing process that's affected its composition. And it's really kind of cool, like how elements in certain areas are available and how the minerals are distributed amongst our planet. Like we will then in turn, go to the surface of the earth and explore how that all happens, like the rock cycle and how it distributes all of these resources amongst the planet. And when you have a foundation like this, you can understand how soil is formed, which essentially for many biological activities on Earth, soil is the start of everything. And, once you kind of understand that process, we will look at all of the problems that we face by pulling all of this stuff out of Earth. It's an issue with great concern to environmental scientists and resource managers alike. So, in the beginning, almost all of the mineral resources on Earth accumulated when the planet formed 4.6 billion years ago. But you got to remember that Earth is a dynamic planet, and Earth's geologic processes form and they break down rocks and minerals, and they drive volcanic eruptions and earthquakes, and they determine distribution of materials. And so, let's examine the distribution of Earth's resources in terms of a geological process. Earth's history is measured using geological time scale. It's hard to believe that events took place 4.6 billion years ago, and they continue to have such an influence on all of our human activities today on Earth. The distribution of chemicals, minerals, and ores around the world, it's part of a function and the process that occurs all these billions of years ago during the formation of Earth. And nearly all of the elements found on Earth today are as old as the planet itself. Roughly 4.6 billion years ago, from cosmic dust, the solar system formed. And then the early Earth was hot, and it was like a molten sphere. And for a period of time, additional debris from the formation of the sun bombarded Earth. And as the molten material slowly cooled, the elements within that spatial layers started to acquire their own mass. And so heavier elements like iron sank towards the Earth's center, and lighter elements such as like silica floated towards the Earth's surface. And some gaseous elements left the solid planet and became part of Earth's atmosphere. And although asteroids occasionally strike Earth today, the bombardment phase of planet's formation was largely ceased when its element composition essentially stabilized. So in other words, the elements and minerals that were present when the planet formed and which distributed unevenly among the globe, we basically got all we have and all we're going to have right now. Some elements that came to the Earth's surface, like silica, those are readily available, and you can find them in sandy beaches, worldwide. And then some things like diamonds, which formed from carbon that had been subject to intense pressure all this time ago, are very, very isolated, and they're very rare. So over the course of human history, this uneven geographical distribution has driven economic and political conflicts alike. Because Earth's elements settle into place, like according to where their mass is, the planet is characterized by distinct vertical zonations. And knowing that slice created this unequal distribution of elements, we can say that the distribution of chemicals, minerals, ores, like all over the world, is part of a function and the process that occurred during the actual formation of the Earth, and is relative to that element's actual mass. Okay? And let's not forget that each of these layers they're very old. The formation of Earth and the actual solar system itself is a process that was 4.6 billion years ago. And this distribution of the elements and minerals today come from that very old process. And so when we take a slice through Earth and we see this vertical zonation, it reminds me of some vocabulary. We have to talk about the core as the innermost layer, and then the mantle, that's the layer above the actual core, and that's where all the magma is there. And the magma is molten rock. This is part of a convection current that's underneath the Earth's crust. And then there's the actual the crust layers, which we call the asthenosphere, the lithosphere, and then the actual crust itself. These layers are composed of outer parts of the mantle and some molten rock. And it just gets more and more closer to dirt, essentially, when you move from the core outwards. So here we can see a slice through Earth, and Earth is composed of multiple layers. We usually describe it as the core, the mantle, and then the lithosphere, which is the top part. And if we were to slice a wedge from Earth, it would cover the width of the United States. So it's essentially 400 miles plus wide. This innermost layer, which is called the core, is about 1,800 miles below the Earth's surface. And the core is this dense mass largely made of nickel and iron. And the inner core is solid, and the outer core is actually still liquid. Above the core is the mantle, and it contains molten rock, or magma, that is slowly circulating in this convection current, which is the lithosphere on top of it is moving on. The asthenosphere, which is a term I have not heard in a long time, is located on the outer part of that mantle, and it is composed of this semi-molten, which is just really, really flexible rock. The brittle, most outer layer of the planet is what we call the lithosphere, and it contains the crust. It's about 100 kilometers, it's 60 miles thick. And the crust that is contained there is very chemically distinct, and the crust is because the crust is more distinguishable than the actual lithosphere itself, it gets a very special name. And it's important to recognize that these regions overlap in a lot of areas, and the lowest part of the lithosphere is also technically the uppermost portion of the mantle. And so the lithosphere is made up of several large and numerous smaller plates, if you remember, which they overlay, and the convection cells that are underneath, that contained within that mantle layer, are pushing and moving those plates. And over the crust there lies this very thin layer of soil, and that's where life gets to exist. That crust and that overlaying soil provide the most chemically abundant elements that make up all of life. And because Earth contains only a finite supply of these minerals and resources, we will not be able to extract them forever. They're not coming out of the planet indefinitely. So, in addition to having mining deposits that cannot be restored, they are also not easily obtained. And so, for both of these reasons, we need to utilize and minimize our mineral resource mining. So, what do you think the reason is for these high temperatures at Earth's core? Why high temperatures where that is directly underneath where we're at right now? And one critical consequence of Earth's formation and element composition is that the planet remains very hot at its center. And the high temperatures of Earth's outer core and mantle is thought to be a result of radioactive decay and various isotopes of elements such as potassium, uranium, thorium, which release heat. The heat from this radioactive decay causes these heat plumes to rise up towards the mantle. And these plumes produce what we call a hot spot. And those are places where the molten material from the actual mantle reaches the lithosphere. And as we shall see in the following upcoming slides here, that hot spots are a very important component of the surface dynamics of Earth. Prior to the 1900s, scientists believed that the major features of Earth, like the continents and oceans, were fixed in place. And then in only 1912, a German meteorologist, whose name was Alfred Wegener, published a revolutionary hypothesis proposing that the world's continents had once been joined together, and he called it Pangea. You may have remembered from sixth grade or even elementary school having to cut out the continents, and if you put them together like a puzzle, they fit together. His evidence included observations identical to rock formations that were on both sides of the Atlantic Ocean, like you can see in this figure here. And the position of these formations suggests that a single supercontinent may have broken up into separate landmasses. And now we have fossil evidence that also suggests that a single large continent once existed in the past. And today we can find fossils of the same species at different parts of different continents that were separated a long time ago and are now separated by oceans. So many resist this idea that Earth's lithosphere could move like laterally. However, following the publication of Wegener's hypothesis, scientists found additional evidence that Earth's landmasses had existed in several different configurations over time, not just one idea of Pangea. So this led to the theory of plate tectonics, which states that Earth's lithosphere is divided into plates, most of which are in constant motion. And the tectonic cycle is basically like the sum total of all the processes that build up and break down the actual lithosphere itself. So the theory of plate tectonics is often called the unifying theory in geology and earth sciences because it relates to so many different aspects of earth sciences. So to sum up here, these hot spots, the high temperature of Earth's outer core and mantle is thought to be the result of radioactive decay of various isotopes, mostly those metals that I've mentioned, and that the heat causes these plumes of hot magma to well up from the mantle and produce hot spots. And hot spots in geology, if that's a place where molten material from Earth's mantle reaches the actual lithosphere.